Hello everybody. This is a video on something called Riemann sums. We have been studying indefinite integrals. Remember indefinite integrals? We've been working on everything from just algebraic, trigonometric, U substitution, change of variable. Well, there's a reason why we've learned that skill, and we've learned that in order to get into something called a definite integral. And Riemann sums is kind of our bridge to that. So a lot of what I'm going to talk about today is my interpretation of history, of kind of how it went down. So this is based on my readings that I've done over the years and what I have learned. But keep that in mind that it is kind of my interpretation to kind of break it down for you for something that's a little bit more understandable. You learned that there were two problems in calculus or in mathematics that kind of spawned the creation of calculus. One was the tangent line problem, finding the slope of a tangent line at a point. And the other one was the area under a curve problem, where they had this funky looking curve that they had to find the area under. And I'm going to have some basic curves here today, but I'm just going to explain to you a little bit about what they did. So they had this curve here, and they wanted to find the area of it. And they had some trouble finding the area of it. So what they did was they broke it down into some Euclidean shapes, some shapes that they knew, namely the rectangle. And if you can see here, there are 4 rectangles here. And what they did is they found the area of each one of these rectangles, and they used that to approximate the area under the curve. Now, you may wonder what kind of a good approximation is with all this space that is kind of missing with these rectangles are inscribed on the curve. Now, this has, these are called left endpoint sums. Left endpoint sums, and it's because the rectangles are inscribed when the left endpoint is on the curve. So that's why they're called left endpoint sums. This is, in this particular case, this is also known as a lower sum. And it's known as a lower sum because the approximation obviously would be less than the actual area under this curve. Let me show you the next one. Ooh, same graph, but this time we are going to talk about right endpoint sums. And it's a right endpoint sum because it's the right endpoint that is the one that is kind of the height of this rectangle. The height of this rectangle. And in this particular case, we're going to have something called an upper sum. And you should be able to see that it's an upper sum because of all this space over the curve. It's going to be higher than the approximation will be higher than the actual area under the curve. Now, how did they do this? Well, if you notice in both examples, and I'm not going to flip back and forth, but in the right and the left endpoint sums, what they had is they had a uniform or a consistent width of the rectangle. So what they did was they found this. In this case, it looks like it's 0.5. From there to there, it's 0.5, and from 0.5 to 1. So they had this width. And they multiplied it by the height of each one of these. So they did length times width. We're going to call it length instead of height. Length times width, plus length times width, plus length times width, plus length times width. That's cool. So we're going to call this delta x. And we're going to call each one of these points, the blue points on the right endpoint, we'll call it f of x sub I. And that just means the y value at each one of these x values. And we can call this delta x sub I if we really wanted to. So really the area was then f of x sub I, which was just the y value. It's this value, this length, if you will, of each rectangle, and multiplied by delta x, which was the width. And in this case, in all the cases, they remain constant, whatever they, in this case, our width is 0.5 for each one of these. So then they would have to calculate each length by just evaluating the function, whatever the function may be. You know, you might be able to guess what this function looks like, and multiplying, and then add them all together. Well, that's cool. As you notice, it's not a very good approximation. There's a lot of space. Even when we do the left endpoints in this case, it's still not a very good approximation. So they found one other type of approximation. What do you think? They did left, they did right. Can you take a guess of what they think the next one would be? Well, it was actually midpoint sums. Midpoint. Yeah, so we had a midpoint sum, or yeah, midpoint sum is where they use the midpoints of each one. Same idea. If you notice, the width of each rectangle is still 0.5, but now they use, for f of x sub I, they use the height of the rectangle based on the midpoint. So they found each one of these guys, f of x sub I, from the midpoint. And they recognized that this was a little better approximation. But then they thought, there's got to be a better way to approximate this other than just using 4 rectangles here. Anyone guess what they did? Anybody? Well, you might think, oh, this looks like x squared. That they increased the number of rectangles. They said, let's do 8 rectangles. Ooh, okay, so we have left endpoint sums. Now you can imagine here. Now looks, delta x, that width of the rectangle changed, got a little smaller, but less space for approximation. They said, well, if we can do 8, let's do 10. Ooh, we can do 10, let's do 20. Ooh, look at that, 20 rectangles. It's getting a better approximation. If we can do 20, now remember, they're finding the area of each one of these things by hand. It's what, 1700s, 18th century, something? Wow, look at that, 50 rectangles. And they continued to do this. And this was, they were using Archimedes' method of exhaustion in order to find this area under the curve. As you can see, it would be exhausting to find the area of all of those rectangles. And it didn't matter if you see inscribed, I can do left endpoint, I can do right endpoint. Ooh, a little over approximation there. I can do midpoint. And we'll learn a little later something called trapezoid, which might, ooh, that looks really good. Trapezoid looks really good. But we'll just leave left endpoint right now. But they continued to increase the number of rectangles. Oh my goodness. How far do you think they went? How far do you think they went? Well, they wanted to go to 1,000? No, I think they wanted to go to like 1,000,000. Or not 1,000,000, 100 million. How many did they want to go? Look at all those. Oh my goodness. Oh, there's an error because they couldn't do it. Value outside legal range. Ooh, okay. But mathematics, in the mathematics of it, they really wanted to go to infinity. Oh no, another error? Okay, maybe 1,000's all I could do. So they wanted to do this. So let's go back to our slide here. And let's go back to our right endpoint sums here just to show you. It doesn't matter, it's true for all. They wanted to take an infinite number of these areas. Well, first off, they used this thing. Oh, I'm going to start a new page here. They did this sigma thing. Sigma, a Greek letter that means sum, of f of x sub I times delta x. Alright, and they wanted I to go from 1 rectangle to n rectangles. And, well, that's so that they can put 10, 20, 30, 40, 50, 80, million, 100, whatever. They didn't alright, well, we want this n, this number of rectangles, to go to infinity. So they used what they learned from before, this idea of a limit, and said, let's take the limit of this sum as n goes to infinity. So now they're finding the area of an infinite number of rectangles. Infinite number of rectangles. This notation right here, the limit of the sum, again, this is my interpretation of history here, this limit of the sum, they got tired of writing all that, and that limit of the sum eventually became the definite integral of f of x dx. That's where that came from. This limit of the sum. That's why this looks like a little bit of an S for sum. And that's where they got this approximation of area under a curve to this definite area under the curve. Well, I hope you enjoyed this little intro to Riemann sums. And again, if you want, you can check out that applet that I had here. If you look up here, there's the thing I really just Googled. If you look where I Googled over here, Riemann sum animation is what I did, and this applet came up. So you can check it out. You can play with all different types of functions in here. You want to do just 2x, you can do, oh no, some errors and legal, okay. Oh, that's why, it's because I was, but x cubed maybe. That doesn't look that much different. 1 divided by x, maybe? Uh-oh, all that. Wonder what happened there. X. So you can play with these functions. Could we do sine x? Oh, it's not. Maybe I need to put a space here. So you gotta play with it a little bit. Parentheses. See, they tell you what to do even. That's cool. Sorry for the little dings. Uh-oh, what's going on here? There's sine x. So you can play around with it. But I'm going to leave now and let you play with that applet if you want. But that's the introduction to Riemann sums and definite integrals. Johnstone out.